Hello. So, since we didn't have enough time to go over the answers of this week's quiz and biochemistry lecture, I thought I'd go ahead and make a quick video to describe it and to go over it here. And that way, on your own, you can go back and review. So, on this quiz, all of the questions were based off of the following scenario that I gave you, which was that there was a new enzyme that had been isolated, and it transfers a phosphate group from ATP to the sugar D-erythrose, using nucleophilic oxygen to attack the ATP. It's also discovered that the sugar D-threose is a competitive inhibitor with respect to erythrose of this enzyme, while sodium vanadate is a non-competitive inhibitor with respect to erythrose. And then I wanted to remind you that V max is equal to kcat times enzyme concentration. So the first question is, name one possible amino acid residue of the enzyme that can be acting as a nucleophile in the mechanism. Well, and then you had to draw the structure of it and give the 1-letter and 3-letter codes for this enzyme. So the best answers to that scenario, and the one that happens the most, is actually serine. So in vivo, we see serine a lot. I would also accept threonine, which is much less frequently used, and then tyrosine. And tyrosine is also used quite frequently, actually, in kinases. Okay, tyrosine kinases utilize the tyrosine. Okay, so those are the 3-letter codes. Of course, the 1-letter code is S, T, and Y. And to draw them, they would look like this. I'm going to draw first the backbone. And then for each one, I'm going to show you what the side chain is. So that's the backbone for all of them. Serine, of course, has a CH2 group, and then the OH, which is what would be the nucleophilic oxygen. Whereas threonine, the alcohol, the OH, is hanging off of the first carbon, the C beta carbon. Okay, and then finally we have tyrosine. And tyrosine is the phenol. So that would be tyrosine. Next question said, to what class of enzymes does this enzyme belong? And I really suggest that you learn the different family names of enzymes that we've been talking about, like transferases, phosphorylases, phosphatases, cyclases, things like that. And there are actually two possible answers for this. The answer that I was shooting for was the fact that I was looking for the the family, the subclass, according to the Enzyme Commission, called kinases, because kinases transfer phosphate groups using ATP or GTP typically. But I will accept also the term ligase, because that is the classification name used by the EC system, Enzyme Commission. But I'll just, once again, want to give you a heads up, especially for later this semester when we go over signaling transduction, and all of next semester when we do metabolic pathways, that you're going to want to remember the term kinase, because that's typically the family that specifically makes phosphate bonds using ATP or GTP. Almost always it's ATP. Okay. The next question, question 5, says, which of the two, if either of the inhibitors listed, would have no apparent effect on kcat or Vmax of this enzyme with respect to the substrate erythrose? If both do not affect kcat, then write neither. So that's really just a way of going about and trying to describe what kind of inhibitors affect which part of the enzyme mechanism. Okay, so I'm actually going to draw the two scenarios out using Michaelis-Menten, and that way we can see which, if either, would affect the kcat or Vmax. Okay, so here we go. Alright, so first off, let's go ahead and draw the one for the competitive inhibitor, and then this will be the non-competitive inhibitor. Okay, so this one's going to be for competitive. This one will be for non-competitive. Okay, and we have V versus S for both of these curves, of course. Now let's put in the inhibitor. Remember, a competitive actually competes with the substrate for binding, so it takes longer time to get there, but eventually once the substrate concentration can get high enough, it can go ahead and reach the same ultimate Vmax and go on to form product. And so let's go ahead and put in the Vmax for both of these, which once again is Kat, is going to be the same. So this one does not affect. Now it does affect Km. Alright? However, for the non-competitive inhibitor, remember that doesn't compete with substrate binding, so it has the same apparent Km. So that's Km. But if we put in the inhibitor now, let's see, nope, right there. So Km would be the same, but Vmax is much lower. So the answer would actually be the non-competitive inhibitor affects Kcat, whereas the competitive does not apparently affect Kcat. Right? So then, if you look at the answer, it said that which one would affect it would be the non-competitive, and that's the vanadate. And so then it says, will the vanadate inhibitor cause a specificity constant to increase, decrease, or have no effect? And briefly state why. So let's go back and show, whoops, didn't mean to do that, what it looks like. And so VS, this is the wild type, so there's Vmax. This is roughly Km. Whereas once we have the inhibitor, which I'll put that in red, it's going to have the same Km. So that's Km. This would be Vmax. Something like that. Not the best. Now it says, what about the specificity constant? So remember, the specificity constant is either Vmax or Kcat divided by Km. So, since this number here is getting smaller and this number is apparently unchanging, it means that the Kcat over Km or Vmax over Km, the specificity constant will be decreasing. So it should be decreasing as the answer. And then finally, it says on the back of the page, draw either the Lineweaver-Burke or the McCabe-Symington plot depicting the effects of the presence of the D3-ose on this enzyme. For full credit, you must label the axes correctly, indicate how you would determine the apparent Kcat, Km, and Kcat over Km for this plot. And so I'm going to actually just redraw that. I've done it once, but I'll redraw it, and that way make it larger. So there's V delta S, not delta S, concentration of S. And in that same color, I'm going to put, this is the wild type. So for wild type, that's Vmax. Kcat, you go one half, for Km, you go one half the way. You see where it hits. You go down, and it's that concentration substrate. Now it says for the the competitive inhibitor, what would it look like? I'll put it in red. For competitive inhibitor, it takes longer but it's going to approach and ultimately make the same Vmax. So for the Km, you go over, and this is the apparent Km for the competitive inhibitor. The Vmax is the same, and whenever it says how to find Vmax, or it says how to find Kcat, technically, Vmax divided by the enzyme concentration is equal to Kcat. And Kcat over Km, I'd accept two answers. One is some people just say you find Kcat and you divide it by Km. The best answer, if you're using a computer to fit it, is if you take the slope of the line of the tangent right here. So the slope of that tangent is going to be equal, so the slope M would be equal to Vmax over Km. And once again, to find the Kcat over Km, you'd actually just divide all of that by enzyme concentration. So hopefully this has helped answer any questions you may have had about this week's quiz.